And
I was able to press that button just now as well, but for some reason it is the warning this meeting is now being recorded didn't come up, but the recording sign is taking place. So I guess someone is recording right now.
Well, let's cross fingers and assume it will work. So still got 5 more minutes. Even though it's starting to record things, we can cut it afterwards. So don't worry, you can talk.
Hearing a pretty awful whirring noise from somewhere, but
yeah. So I just disabled right now. I disabled the option to emit a sound when someone joins or leaves the room. I guess it was.
No, I'm hearing like a fan noise.
Oh. Yeah. So
whatever.
Oh yeah, right. So do I. So
if I mute,
yeah. Oh yeah, there is not anymore this noise. So which means that it's. So is it? Do you have a fan?
Yep.
Yeah, so it's my computer fan, which every time I share my screen is a bit louder, but for me it's not so loud. So
okay. Well, I guess we can deal with.
While you are talking, it seems that it's being filtered out. But if you're not talking, then we can hear it.
Yeah. So, please never stop talking.
Okay.
Still got a few more minutes. Well, I'm not going to ask you how are things in France because, well, I know it as well. But I'm glad in the US, your beloved president is going well. So I guess, yeah, the number of participants has stabilized. So we'll soon be able to start.
Okay, we still have 2 minutes from my watch, but that's much.
Yeah, but do these people who just arrive on time deserve to listen to the start of your talk? So, okay, so let's start. So hi everyone. So welcome to the 25th version of the seminar. So today we are welcoming Paul-Elliot Anglès, and I'm glad to be French to be able to pronounce his name. So he's going to talk about the computable strength of Milliken's tree theorem and applications.
Thank you. Hello, everyone. And so thanks a lot first for the invitation and also for everyone for being here. I will present a recent work that I did with Peter, Damir, Benoit, and Ludovic on the computable strengths of Milliken street theorem and applications. So my talk will be divided in two parts. The first part is the presentation of so the two applications, Devlin and Rado graph theorem, and how they are proved using Milliken street theorem. So the combinatorial part only of these three theorems and their links. And then I will show the results on the computable strengths of Milliken street theorem and its two applications. So first, consider the well-known Ramsey theorem, which has been extensively studied in reverse mathematics, and which is a statement about the integers. So now, so it states that if you color n tuples, so the n element subset of the integers into finitely many colors, then we can find an infinite set, so that if we take all tuples taken from this set have the same color. Now what happens if we try, instead of having so the integers which don't have structure, add structure to this statement? So we will start with a countable L structure on a certain language, and we will have a coloring of the n element subset of A. And then what we are looking for is not anymore just an infinite subset, but a subcopy. So a substructure which is isomorphic to the original structure, on which F is homogeneous. So this statement first is really, so when we take the language, an empty language and the trivial structure, it is exactly Ramsey's theorem, because a subcopy of an infinite set with no structure is just an infinite subset. However, this statement is false on many structures. So let me give you an example. Take the structure of graphs and a structure of a graph which is non-trivial. So there exist two vertices that are linked and two vertices that are not linked. Then if we color two tuples depending on whether they are linked or not, we will have that any subcopy of A must be non-trivial and thus must have two colors. And this example can be given whenever we have a structure that has two non-isomorphic substructures of the same cardinality. We give the coloring which given an element subset gives a color of the color corresponding to the substructure, and any subcopy has at least the number of substructures. Okay, so what we can do to have a statement that is still meaningful but is true in more structures is to allow more colors in the output, which we can do by just adding this, relaxing the requirement of being monochromatic to taking at most L colors. And this statement here, we will call it Ramsey statement for structure A, n tuples, and L colors allowed. Okay, so one remark is that in this statement, we are coloring n element subset of A, which it will be a bit more natural instead to color the substructure of a given structure. So we will define the set of finite subcopies of F inside A, like this. So for instance, in the example with graphs, we could take F being two elements which are linked, and we will color only the two tuples which are linked. Even with this statement where we color this set which is included in this one, we will need to allow more colors very often. So we won't focus here on this distinction, the important part is that there exists a finite number of colors that does not depend on k, and we can always reduce to this number of colors. Okay, so now when is this statement true? So when is Ramsey's statement for structure A and tuples true? So when it is true, we will say that a null structure has finite big Ramsey numbers. So a null structure has finite big Ramsey number if Ramsey statement for structure A is true for every n with some ln, which some l key, which depends on l. And so it has finite big Ramsey. It must be true for every n. And the optimal such ln is called the big Ramsey number for n tuples. So the big Ramsey number for two tuples is the smallest number of colors that we can always reduce to for n tuples. Okay, so now we need a few examples. I said that more structures have finite big Ramsey degrees, and I will give you two examples of structures with finite big Ramsey degrees, which are DLO and Rado graph. So let's start with DLO, which stands for dense linear ordering, which is a famous structure. So for instance, the rational are DLO, but in terms of structure, it's an structure on the language of the order, which is a linear order and also satisfies that for every x and y, there is some point below x, some point in the middle of x and y, and some point after y. This structure is satisfies many things, and the two important are universality and homogeneousness. So, which I give the definition now. So, an L structure A is universal for a class of finite structures C if every element of C embeds into A, that is, A contains as substructure all the elements of C, all the finite structures of C. And homogeneousness, which is a structure is homogeneous if when you started building an isomorphism between two finite substructures of A, so they are locally isomorphic, we can extend this isomorphism into an automorphism of A. So, which is a useful property to say that when things work well locally, you can extend it globally, and you can thus build an automorphism just by adding points one by one in a back and forth construction. And the DLO structure, every DLO structure is universal for the class of finite orders and also homogeneous, which has a consequence that they are all countable. All the countable are isomorphic. So there is only one dense linear order up to isomorphism. Okay. So now we continue with the study of big Ramsey number for this structure, DLO. So we start with looking at maybe lower bounds. So first we had the example of for a lower bound on the big Ramsey number just by coloring depending on the substructure. And here, any n element linear order is isomorphic to any other n element linear order. So there is only one substructure with cardinality n, and but however, the big Ramsey number is not one. And I'll give you just now an example of how we can need more color. So for instance, consider a DLOQ, so any DLO, and the two coloring, which will color X, Y, depending on X being smaller than Y, but for X being smaller than Y for the natural numbers. So we have this relation on natural numbers, and Q is a subset of the natural number as it is countable or can be seen. We have this property which enables us to distinguish X and Y, and thus even if two element linear order are isomorphic, we can still make a distinction with this F. And now, if we take any sub-DLO Q prime of Q, we can find those three elements satisfying this and this, because there are finitely many elements below X. And there are infinitely many elements, so for natural numbers, but there are infinitely many y0 less than x for q, and infinitely many y1 greater than x for q. So we can find those three, and this tuple of y0 and x will have one color, and this tuple will have the other color. So if it exists, the finite big Ramsey number of two tuples for Dunstian ordering must be at least 2. And Devlin theorem states that yes, the DLO structure has finite big Ramsey numbers, so we can always reduce to a finite number of colors independent of the initial number of colors, only depending on the cardinality. And the values are these ones. So for one tuple, it's 1, and for two tuple, it is 2, meaning that this example here is the optimal example, and then 16 and 272, a value which is counted by just counting a certain combinatorial structure called the Joyce trees. Okay, so this is all for DLO. We will now switch to radograph and see that even though it's for graphs, it is very similar to dense linear ordering. So the radograph is a graph, so it is a structure with a binary relation E that satisfies the following. If we take two finite groups of disjoint vertices, we can always find a vertex V in the graph, such that V is linked with all the elements of F0, and V is not linked with all elements of F1. So we choose the one we want to be linked to, we choose the one we don't want it to be linked to, and there exists a witness of this. So once again, G is homogeneous and universal for the class of finite graphs. So this is why it shows many properties with the DLO, and also this is why you call we sometimes say Z radograph, because it is unique up to isomorphism. Okay, so the example we had before, coloring xy depending on whether x is linked with y or x is not linked with y, works here. So if we use this coloring and take any Rado subgraph of G, as it is a radograph, it will have two linked vertices and two non-linked vertices, and thus it will have the two colors used. So the big Ramsey number of the radograph for two tuples must be at least 2. And Laflamme, Sauer, and Buksanovic showed that the radograph has finite big Ramsey numbers. And Larson computed the exact, later computed the exact values, which are 1, 4 for two tuples. So this example is not an optimal one. And then 112 and more. Okay. So two similar structures which are homogeneous and universal, and they both satisfy that they have a finite big Ramsey number. How to show that they have a finite big Ramsey numbers? The two theorems share a very close structure, and the only difficult part, so the combinatorial core of those two proofs, is the use of Milliken's tree theorem. So we can reduce both theorems to Milliken's tree theorem, which I present now. So Milliken's tree theorem is obviously a theorem about trees, but not the tree we usually consider in computability. That is, they are not closed under prefixes. Instead, they are closed under longest common prefix, which we can see as the meet inside this space. So this space can be seen as a tree. So it has a meet, and a tree is a subset of this which is closed under MIT or under longest common prefix. Then all the other definitions are quite natural. So the level of a node is the number of strict predecessors. The root has no predecessor, so it is of level 0. Something that has not only the node as the root as a strict prefix is of level 1. And the nth level of a tree is a set of nodes of level n. The height of a tree, so it is omega when the tree has unbounded height, and if the maximum level of the tree is n, then the height of the tree is n plus 1. So for instance, if it has only a node, the node is of level 0. The root, sorry, if it has only a root, the root is of level 0, and thus the height is of level 1. And then k branching is just having k compatible extension, which is what we expect from being k branching. So here we define the notion of space of Milliken's theorem. We will now define the notion of subspace, which is strong subtrees. And a strong subtree is a subtree of a tree T, which has moreover, which preserve also two things: the levels and the branching. By levels are preserved, I mean that given two nodes of the strong subtree which are the same level in the strong subtree, they will be in the same level in the original tree as computed in the original tree. In other words, we can have a function which maps the level in the strong subtree to the levels in the original tree. And also the branching is preserved, meaning that if some node was k branching, it is still k branching. And then we write S alpha, S for strong subtree of T, for the set of all strong subtrees of height alpha. A picture to illustrate this. We have here the non-dashed line, the plain line are the levels of the strong subtree, so level 0, level 1, level 2. The corresponding level in the original tree are F0, F1, and F2 for F being the level function. And this node here was k branching in the original tree, so it is still k branching in the strong subtree, and thus it has to branch directly because it is mid closed, and then each extension in the original tree has a unique extension in the strong subtree. Now we have the notion of space subspace. We can state Milliken's tree theorem, which is very close to Ramsey's theorem again, but this time with trees as a space and strong subtrees as subspace. So given a tree height n and the coloring of the strong subtrees of height n of T into k colors, we can always find a strong subtree of infinite height such that f is constant on the strong subtrees of height n of S. So we really see that it's close to Ramsey's theorem. Instead, it's coloring strong subtrees. Now we can continue and see how Devlin theorem and Rado graph are both implied by Milliken's tree theorem. So we will start with Devlin's theorem, so about the dense linear ordering. And we have the following definition, so of an ordering of strings of 2 to the less than omega. We say that sigma is less than tau if either sigma extends the common prefix to the left or tau extends the common prefix to the right, so left being 0 and 1 being right, which can happen in those three possibilities. Either sigma extends tau and it extends it to the left, or they are incompatible, or they are compatible and this time tau is bigger and it extends sigma to the right. And so the analogy just being on the right of is preserved for every picture. So you can just think of being to the left or being to the right when drawn into a tree. Now, for the proof, we will use 3 embeddings and prove 3 embeddings in order to go from the space of DLO to the space where we can use Milliken's tree theorem, and then back to the space of Devlin theorem. So we first prove that T with this relation that I just defined embeds into Q. Also, S as any strong subtree of T, T being a perfect binary tree, embed into T, and then Q embeds into any strong subtree of a perfect binary tree when it has this relation. So how to prove this? Three embeddings. So the first embedding is just because that Q is homogeneous and universal for the class of finite orders. This is an order, so we can always embed it into Q. The second is just because this is a relation, so being a substructure is just being a subset of, so the relation does not depend on S or T, so it is a substructure just as a subset. And finally, we have to prove that Q is a subset of S less than Q. S less than Q, S is a strong subtree of a perfect binary tree, and thus is a perfect binary tree itself. And as a perfect binary tree with this relation, it is already a dense linear ordering. So Q, which is dense linear ordering, embeds into this, which is a dense linear ordering. They are even in bijection. Okay, so now given these three embeddings, we will be able to go to use this one to be able to apply Milliken's tree theorem and then come back to Q. So we start with the coloring of the n tuples of Q into K colors. We will use the injection I here to have a coloring of the strong subtrees that depends on this one, on the original coloring. And as you can see here, we are coloring strong subtrees of height 2 and n-1, and not only strong subtrees of height n. So the reason is that, for instance, two strings defines three heights: the height of one string, the height of the other string, and the height of the meet. So if we, for instance, with 2 had decided to color the height 2 subtrees, we would be able to take into account the color of Q, Q0, Q, Q1, and Q0, Q1, which are always either of the same height or compatible. So we don't take all the possibility of values of F into account. And this is why we have this 2n-1 here. So F is defined on heights for n equal 2. It is height 3 strong subtrees, and we cover all the possibilities. Okay, now we have a coloring of height 2n-1 strong subtrees, so we can apply Milliken's tree theorem and have an S which is homogeneous for Ft. And by the last embedding, we can have an embedding of Q into the original Q, which, because it is a subset of S, and the fact that this is monochromatic for Ft, Ft includes at most this number of colors, so we have finitely many, which does not depend on K, number of colors used in the end. And thus, we used only Milliken's tree theorem as a complicated thing, and we proved Devlin's theorem. Okay, so this concludes for Devlin. Now for Rado, it will be very, very similar, but we still go through it to see that it is similar. So we again define a relation, this time called EPN because it's a binary relation, and Pn stands for passing number as defined by Sauer. So EPN, so sigma is linked with tau if either sigma is less than tau. So if the smallest one, so if the longest one at the height of the smallest one is a 1. So it is the same here. The longest one at the height of the smallest one, tau, it is a 1, which can happen in those cases. So here sigma and tau are symmetric. We can have can exchange them. So either they are compatible and it goes to the right at the position of the smallest one, or at the position of the smallest one, it goes to the right, or at the position of the smallest one, it goes to the right. Okay, so this is the definition of EPN, and we will have the same embeddings. So TEPN embeds into the Rado graph G. Any strong subtree of a perfect binary tree embeds into T, and G embeds into any strong subtree of a perfect binary tree with relation EPN. So the first is still because G is also homogeneous and universal for the class of finite graphs, and this is a graph, and so we can prove the embedding. This is also because it's a relation, so and it does not depend on the context. And finally, this is different, and we have to do something to prove it. And I'll show you quickly how it's done. So we want to embed a graph into the perfect binary tree with the relation EPN. So for instance, start with the red node. We can put it just for now. There is no requirement, so we can put it at the root. Then we want to embed to have the image of orange. Orange is not linked with red, so by EPN it must be on this subtree here, on this part of the tree. So we can put it again at the root. Now blue has to be linked with red and orange. So it has to have go on the right here, and at the level of orange, go to the right. So we can put it here. And now we see we have one level per things we already put. So we put the next one, for example, green, to the next level, and according for the previous level to how it is linked or not. So for instance, green will go here. It is not linked with red, not linked with orange, but linked with blue. Okay, so we have our embedding, and then the proof is exactly straightforward from the previous one. So we start with the coloring. This, by the injection, yields a coloring of strong subtrees of height 2n minus 1. Then we use Milliken's tree theorem to get S on which F is monochromatic, and the fact that G is a substructure of this gives us subcopy of G inside G using at most finitely many colors, which concludes the proof. Okay, so as we can see here, the two proofs are really similar, and the only parts that differ is here and here. So we can extract from this some kind of meta theorem, or just remark from the proofs, is that whenever we have a structure and we can prove that there is a tree and a set of relation R, which are the relation we defined at the beginning, such that TR embeds into A, so SR embeds into TR and A embeds into SR, so the three embedding. Then by Milliken's tree theorem, A has finite big Ramsey numbers. The first one is often by being homogeneous and sufficiently universal, so universal for the finite substructures of TR. The second one is just because R is a relation and defined on something which is not dependent on S and T. And finally, the last part is where you need to do a clever choice of relation, and so that this is true and depends on every theorem. Okay, so now we see that during this proof, the only difficult part were the use of Milliken's tree theorem. Otherwise, it was computationally very easy. So if we want to understand the computational strengths of those theorem, we need to understand the computational strengths of Milliken's tree theorem, which is already important on its own. So we continue with the reverse mathematics part about its strengths. So first, the acronym, so MTTN for Milliken's tree theorem, and the N stands for the height of the strong subtrees. Usually, we compare to a previous framework, so there is a big 5, which is available to see how strong it is. but we also have Ramsey's theorem. And in the case of MTT, Milliken's tree theorem, it makes sense to compare it to Ramsey's theorem as it is a very close statement. So our first result, so with Peter, Demir, Benoit, and Ludovic, is that Milliken's tree theorem is provable using ACA knot, which which reflects here as an equivalence here, as MTT3 implies RT3 just by coloring, remarking that when we color only depending on the levels, it is exactly Ramsey's theorem. Or maybe when we color a unary tree where each node is one branching, it is exactly the same as Ramsey's theorem. So the difficult part is proving MTTN provable in ACA knot, which is our theorem. And let us have a sketch of how it goes. So first, I need to show you how the proof of Milliken's tree theorem goes, and then we will see how it can be made so that only arithmetical objects are considered. So we start with tree T and coloring F. The first thing that we will do is to to take a strong subtree S of T on which F is stable. So with stable just as in a Ramsey's theorem, but it is different. So I need to define what I mean by stable. Stable means that whenever we take a beginning of construction of a strong subtree of height n, that is a strong subtree of height n-1, in this case n is 3, so n-1 is 2. Whenever we have a beginning, there exists a threshold and a color, after which, for every completion of F, where the new level that we add is after L, so sufficiently far away, if this is really a strong subtree of T, then the color is CF, which depends only on F. So this is stability. The last level is not fixed, and if it is far away, it will have a limit color. So I said limit color, so of course, from F, here we can associate CF. So this stable coloring yields a limit coloring, and the limit coloring is on strong subtrees of height n-1. So we can apply MTT n-1 to get S prime homogeneous. Of course, there are some things to do, like shrink, remove things so that it is only, so we know there could be some levels that we want to remove, but I won't focus on here. So the only part which remains really unclear is how to have a stable coloring from arbitrary coloring. And this will be by iterating a kind of pigeonhole principle. So we take some F, and we take a strong subtree where the limit coloring exists, and by applying some kind of Milliken's tree theorem for height 1, because we can see that it is when F is fixed, there is only one H that we consider. So it's some kind of height 1 thing. So however, Milliken's tree theorem for height 1 does not suffices. We need a version of Milliken's tree theorem for height 1 on products of trees. So we define S alpha of the tuple T0 to TD-1 to be the collection of tuples from where each is a strong subtree. So S0 is a strong subtree of T0, and dot 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 SD-1 is a strong subtree of TD-1, but also using a common level function. That is, for instance, S1 of T0 T1 is one node from T0 and one node from T1, but at the same level. And then Halpern-Loschly's theorem is exactly Milliken's tree theorem, but for this notion, So we have T0 to TD minus 1 infinite trees, and we have a coloring of the strong subtrees in this sense of height 1. So nodes from one node from each tree, but at the same level into k colors. And then we can find strong subtrees showing a common level function of this, so that f is constant on this. So if the statement is not clear, it is just Milliken's tree theorem for height 1 in a product version. Okay, so now we can try to see how arithmeticality propagates in this proof. So we start with TF computable. We could prove with the team that HL is computably true. So the height 1 product version is computably true. And by iterating it in some way, we can show that because it's uniformly so, the cohesive version admits delta 03 solution, so arithmetical solution, and we can get here for stability S arithmetical. So here the definition of F-lim from F and S is given here. It is just an arithmetical statement. So S and F-lim are arithmetical. Now, just by induction, so our induction works like this. MTT1 is computably true. This is true by H, the fact that HL is computably true. And now we suppose MTTN minus 1 to admit arithmetical solution. As we just apply MTTN minus 1, we get S prime arithmetical. Okay, which concludes the proof of this. So we can go back to our summary of the implication. We have seen how this is implied by SCN not. And during this proof, we also show that MTT1, which is equivalent to HL, and also to RCA not. So it's at the lowest possible level because it is computably true. So we know for MTT3, we know for MTT1. What about MTT2? So first, MTT2 implies MTT1, of course, and also implies RT2 just by taking unary trees. But we don't. So the question that remains is whether MTT2 is equivalent or not to MTT3, or does MTT2 implies ACA not? And we could prove again with the same team that they are not equivalent. MTT2 does not imply ACA not, and thus the structure of strengths for Milliken's tree theorem is really the same as the structure of strengths for Ramsey's theorem. So how could we prove this? So the structure of the proof is the same, but this time what we need to propagate through the steps of the proof is coin avoidance. So we want to start with something that does not compute 0 prime and continue up to having a solution that still does not compute 0 prime. So we start with TF coin avoiding, and we had the following facts. So the first fact is HL admits coin avoidance, which is true because it is computably true. And then we need to iterate this to have that CMTTN admits coin avoidance. And this was really complex. We had to nest the application of HL in a clever way so that we could use compacity at some point and get coin avoidance. It's a rather technical proof, but it works. So we can have get S and F with F stable on S so that they are coin avoiding. They don't compute 0 prime. Now, F-lim is defined the same way as before, but it is arithmetical in S, which is a problem. It can be more powerful to know the limit coloring than just to know the coloring. So we need a stronger statement than coin avoidance for MTT1. And in fact, we also could prove this stronger statement, which is a strong coin avoidance. So given any instance of the hypermostly theorem, we are able to find a coin avoiding solution. And thus, this is an instance of MTT1, so of HL, and we can get S prime coin avoiding, which concludes the sketch of the proof of why MTT2 does not imply ACN0. The hard part being so proving this theorem and proving this theorem. Okay, so we now know most of the things we want for Milliken's tree theorem. So we can start to apply those things to the implication Devlin and Rado graph theorem. Okay, so first we name them. So RGN and DTN denotes respectively the Rado graph theorem and Devlin's theorem, and with optimal bounds. So if we allow more colors, so if we just consider Rado graph is having finite big Ramsey degree, is different than having the optimal finite big Ramsey degree. And also, I recall that two strings define 3 levels. So in order to prove RG2 and to prove DT2, we did not use MTT2. We don't have that RG2 is a consequence of MTT2 and thus is less than MTT3. We always used MTT3 because 2 strings define 3 levels as in this picture. So the first is the Rado graph theorem, which we showed that RG2 is equivalent to ACN0, RG1 to MTT1, but RG2 is in the middle. It admits coin avoidance. That is, it again shares the same structure as Ramsey's theorem, and in some way, the fact that so here RG2 is somehow a statement about 2 things because we only have 2 elements of the graph. But in other way, it's a statement about 3 things because we have the meat and the 2 original things. So we cannot use the Jokic argument to prove that RG2 is a statement about 3 things and thus imply ACN0 because they are a bit too entangled. We cannot do what we want with the 3 levels defined by 2 elements of RG2. And contrary to this, we could prove that DT2 already implies ACN0. So DT2, even if it's about only 2 elements of dense linear ordering, is somehow a statement about 3 things, the 3 heights defined by the 2 elements of the dense linear ordering. And thus, DT2 implies ACN0, and we have a different behavior with Devlin theorem and the Rado graph theorem. We could also consider what happens if we increase the number of colors, but the summary is already quite big like this. So I conclude with this, and I thank you for your attention.
Okay, thank you very much for the talk. So does anybody have questions?
What about, excuse me, what about MT2 and TT2 too?
MTT2?
Yeah, MTT2 and TT2 too.
Oh, versus TT2? The tree theorem?
Tree theorem for pairs.
Yes. So tree theorem is at least Milliken's tree theorem implies the generalized tree theorem, which also implies a tree theorem. So MTT2 implies TT2.
Ah, I see.
I'm-
Conversely, do you know?
So
I think it's unknown, the
It's
reverse
unknown?
implication. So it's known that Ramsey theorem for pairs does not imply the tree theorem for pairs, but it's
Right.
not known whether the tree theorem for pairs implies Milliken tree theorem for pairs.
I see.
yeah.
Okay. Thank you.
Any other questions?
So why is it? Why is it that Ramsey's theorem for pairs does not imply either Milliken MTT2 or TT2
So why Ramsey theorem does not imply MTT2?
for pairs? Yeah.
So MTT2 is a stronger statement because you can have, so with the same levels, you can have multiple strong subtrees that, so it does not imply because, so statements are different and MTT2 is stronger as you can have a lot of different strong subtrees with the same two levels, but with different colors. Okay, so why?
But if you
want a literature reference, right? I mean,
Yeah.
We know Ramsey's theorem doesn't imply the tree theorem, the old tree theorem.
Yeah.
And that's a consequence of Milliken's tree theorem.
Yeah. Yeah.
Right. No, I understood. What's the I don't know the proof of how would you prove it? Is it a calculation of the number of jumps? That isn't sufficient on its own.
So I don't know because it goes through the proof of the fact that RT2 does not imply TT2, and I don't know this proof. So
Well, this is a rather complicated proof involving forcing and preservation of some kind of specific notions which cannot be like easily explained like that. But so it's not by a simple calculation of the number of
Right.
jumps, because when we make a separation, so
right. No, it can't be just a calculation. That was what I.
Yeah,
It's an arithmetical difference. Yeah.
It's a forcing separation and preservation of a weakness property. That's.
And does it look like it should be any easier to get the proof for MTT2 instead of TT2?
From which theorem?
So the argument that RT2 does not imply TT2, you just described in some, but would it then be, would it be easier to get that it does not imply MTT2? Suppose you went for a direct proof is what I'm saying.
Yeah.
Is it essentially the same, or you can't tell? Never. Why bother to think about it?
Yeah, I don't know.
It'd be interesting to think about, I guess, but it's, it could even be that TT2 and MTT2 are equivalent. So.
Yeah, so so the question is whether there's some difference that shows up here.
Yeah, well, I guess a related question is, we know that RT2 admits low-2 solutions, and so there is a model of RT2 which has only low-2 sets.
Yes.
And I think it's also true for the tree theorem for pairs, but it's not known for Milliken tree theorem for pairs. And my guess is that it's not true, actually. So it may not have low-2 solutions. And it would be somehow a simpler way of proving.
That would be a simpler proof, right? If you knew that, that would.
Yeah, my guess is that it does not admit always low-2 solutions.
So that would be a sort of simpler structural proof. I don't know if the proof would be simpler, but
maybe
the reason why it's different.
The reason, would be intelligible.
Right.
But I think so. CT, you have been working on this statement as well, right? And I think maybe you know whether it admits low-2 solution or not. Have you been looking at this?
We're only looking at HL rather than from the B sigma 2 point of view. Yeah.
Oh.
Not Milliken.
So more the induction strength of, yeah. Okay.
I have a question. Maybe it was answered in the talk, but I didn't catch it. If so, is your bound of delta 0 2n minus 1 on the solutions for computable instances of MTT NK, is that bound optimal?
It's optimal. I don't think we have a proof that it's optimal.
Actually, we don't know.
Yeah, we don't know.
So because the whole thing is for Ramsey theorem, when you make the inductive proof, you make it inductively by the notion of pre-homogeneous sets, which is obtained by a PA over 0 prime degree. And so it only increases the level in hierarchy by one more level, because there are low PA degrees. But in the case of Milliken's tree theorem, the notion of pre-homogeneous sets, which is still defined, which can be still defined, so it's not known to be computed in a PA over 0 prime degree. Actually, it's only known to be able to be computed by a 0 double oracle, and it's still unknown whether this is optimal or not. So, any other question? Okay. So, if there is no more question, I think we are going to, as usual, split the group into breakout rooms to have more informal discussions. So let's wait just a little bit to see who remains so that I can split into the right number of rooms. And we can stop recording.